this is what I will call the eikonal equation. My vector field is divergence free and of a unit norm. Okay, so maybe for you the eikonal equation is something else, and in fact you can always like decide to say, because you are in 2D, that a divergence free vector field is just a gradient rotated by p over 2. So this is what I write like this, the gradient rotated by p over 2. And then I'm just saying that the grad of phi is of norm 1, and this is what is usually called the eikonal equation. But in this talk, I mean, yeah, that's perfectly equivalent because I say my domain is simply connected. And this talk I will choose to work more on this formalism, but you have to recall this is the same thing. Here this is more like the Hamilton-Jacobi side of things, and here this is the scalar conservational side of things. Yeah, so hence the name eikonal equation, which was more given to the equation. And what happens with that solution, with that equation? Well, if you look at smooth solutions, they are very rigid. Because what happens is information is transported along characteristics, and so basically if you have a smooth solution, you have no choice that the vector field has to be transported along lines that are perpendicular to it, right? But if at some other point there is another direction, you see when characteristics enter into each other, you have a problem, you create singularities. So in fact, smooth solutions are so rigid that they're not that interesting, because in practice, you cannot ensure that they exist. So that's why people have been looking at weak solutions. And with weak solutions, you have the opposite problem. Weak solutions are very, very flexible, and basically anything can happen. And let me just give first a very simple example of a weak solution. So imagine you have the full plane, and you can decide to restrict it to a bounded domain in that situation. And you just ask, you just take a vector field that is constant on one half of the plane, constant in the other half, and if you do things right, that is, if you ensure that the component that of this constant here, this constant vector field, that is perpendicular to this jump set are the same. So basically, the first component in the direction is continuous. Then, in fact, this kind of thing is a solution to this equation. Because when you take the divergence, well, the derivative in the x direction, since you are constant, it's 0. And the derivative in this direction, since the first component is constant, you don't see it either, right? So this is a very simple, weak solution, not smooth, of this equation. And even a particular case of this would be just something like that, right? And if you take this solution, which is a weak solution, you can think of many other weak solutions that agree with it outside of the compact subset, but which are very different. For instance, you can play with domains like that and add constant things like this. Well, it's not very hard to check that that this kind of stuff is actually a weak solution. And you could imagine like adding more of these weird things at all smaller scales and building a lot of very wild solutions. So this is just to tell you that weak solutions can be very basically anything can happen, as I said, and and so in general this is well, this is an issue, because if you have a physical model that is modeled by something like that, you don't want that everything be possible, right? You want really to have something definite. And so of course, usually what people do is they consider viscosity solution. So this is a beautiful theory that was developed by Crandall and Lyons, and which ensures that if you fix some boundary conditions for phi here, then you have uniqueness, okay, and existence under certain conditions. But in my case, I will be interested in some weak solutions, so I will restrict a bit, not all weak solutions, but just some of them, but the class will be a bit wider than just the viscosity solutions. And these are the solutions in my title, the solutions with finite entropy production. Okay. And before telling you what this means, I want to motivate this, to say where that notion comes from, and why we want to study this class of solutions. And the motivation is a model which people in math call the Aviles-Giga energy. This is just like your favorite phase field model or phase transition model or whatever you want to call it. Ginsburg-Landau energy, Allen-Kern. Well, it has this kind of energies have many names, but here the difference is that you are adding this constraint, that you are looking at vector fields that have zero divergence. And in fact, this changes a lot the behavior of the minimizers, of sequences of bounded energy, and this is why questions around that energy have really puzzled a lot many mathematicians for many years now. Why? Okay, from the physical point of view, and from the point of view of maybe designing new materials, what's the motivation for looking at this? Well, there are many. This is a model that pops up either really exactly like that, or like with similar features in many physical applications. The reason why Aviles and Giga first introduced it was in relation with smectic area liquid crystals. They were actually looking at a model introduced by I think Kleeman and Parodi, and this is a simplification of that model. Okay. Also, you can see like a similarity with micromagnetic thin films, where I mean, this is really just an analogy. Why? Because here my epsilon in my model, so this is like the characteristic length scale of the model, and you have to think of it, because I call it epsilon, as something very small. So you see that if epsilon is very small, and if I want to take, say, configurations that don't have too big an energy, then this should be very small, right? So you probably want M to have modulus very close to 1. And in micromagnetic thin films, what would happen is that the unknown typically would have exactly modulus 1, but the divergence would be approximately 0. And so you have similar models there, and you can expect similar features. Another occurrence of this energy is a modeling of thin film blisters, which is related to, I think it was introduced by in a paper by Joya and Ortiz, and in fact this is exactly this energy that pops up. Maybe more in terms of this phi here, but at the end this is the same thing. So this is another motivation, and the last motivation comes from some equations describing pattern formation, actually in a very general sense, but I think the first occurrence of it is related to some pattern formations in Rayleigh-Bénard convection, and here the names are Cross and Newell who introduced. So this is more of a dynamical equation here, but you could think of it as say a gradient flow associated to this kind of energy. So in all these things, this model pops up, and that's why it's also interesting from the physical point of view. And all right, let me say a little bit what is known about this. So many people have worked on this model. And I don't think I will have time to explain in depth all the subtleties and all the results that are relevant here, but I will just cite the ones that are important for me to explain what I want to explain today. So the first thing to understand is I wrote this thing that m is approximately of modulus 1, because in the limit I want to recover this equation, right? I want to motivate why I'm looking at this equation. And in order to be able to do that, you need to say, okay, let's take a sequence m epsilon that I put into this energy. I say it's a minimizing sequence, for instance, or it has bounded energy, and I want to be able to pass to the limit and to say that in the limit, this almost equal is actually unequal. For this, you need to have some form of strong convergence. So this is in fact the first thing you need. You need some compactness statement, and this is due to several teams of people. Ambrosio De Lelis and Mantegazza. At the same time, there is also the same result by De Simone, Bob Cohn, Stefan Müller, and Felix Otto. And I think just a bit later, also another proof by Jabin and Pertam. So many people have proved this. And here is the result is if you take a sequence m epsilon, which has bounded energy, then you actually have convergence in a strong sense in L1, and then all LPs, but it's important that we have in L1. And as a consequence, because if you have, okay, of course, here I need to take a subsequence. As a consequence, I also have a subsequence that converges almost everywhere, and I can pass to the limit in that kind of relation, this almost equal, right? So the point is, since you know that you have this strong convergence, M solve this equation, right? So now I have justified the fact that I will be looking at solutions of this equation. Let me just say a bit more about that. See, if you have the assumption that the energy is bounded, it doesn't give you like a bound on the integral of the gradient squared, because there is this epsilon in front. So it's really something non-trivial to be able to show that you have some strong convergence in some LP space. And those are actually quite deep results. All right, so from now on I have this solution of my equation, my eikonal equation. And of course, I mean, once you know that, now you know a little bit what the limit might look like. But as I told you, I mean, we don't know much because solutions of this equation, there are many of them. I don't know what's this. So yeah, let me write down the conjecture. So then you want to understand maybe what does the limit energy look like. And this is a conjecture that has been open for quite some time now. I'm going to state it quite roughly, but I hope you get the feeling about it. So if I suppose, say, my m epsilon, they are minimizers of the energy. So when I say minimizers, you have to understand with respect maybe to some boundary condition or something like that. I don't want to be very precise about this because I won't be precise at all. But the idea is that if you have a sequence of minimizers, their energy, it should concentrate. So when I say concentrate, I'm assuming that is as epsilon goes to 0 along a set which should be 1D. This is the conjecture. And moreover, if you know that it should converge to an energy that looks like that, well, there is a constant which is universal, say 1/6 or 1/3, I don't know what. and then the energy is concentrated only on this jump set, right? And what does it do? It looks at the jump. So you have a jump on one side of the jump set, you have a value on the other side of the jump set, right? And you take the cubic power of it, right? And then you integrate along this jump set, and you suppose that it is a 1D jump set, right? So this is what it looks like. Of course, when I'm writing this, I'm assuming implicitly that the limit m, you know that it has a 1D jump set and that you can write that kind of thing. So where does this come from? It comes really from looking at this kind of configuration here that I draw here, right? And looking at a 1D transition. Okay, this is this curve you should think of it as above, right? At the 1D transition, say at scale epsilon, you take the type of 1D transition that has the least energy possible, and this gives you this kind of cubic power, right? So this is looking at 1D transitions. This is quite classical in this phase transition problems. What's annoying here is this cubic power, because as I said, so this conjecture, you see, I was only able to state it, actually to write down the energy, knowing a priori that I have a good structure for the limit. So I have a 1D jump set, I can define values on each side of the jump set. So I'm assuming a priori that I know already a lot on the limiting configuration. And in fact, this is precisely what's missing to complete the conjecture. I mean, if you assume a priori that you know that the limit is something that has this kind of nice structure, then you can prove this. It's not that easy, but people have done it. So really, this kind of thing, this is okay if you know a priori that M has a good structure. Right. So what does it mean, a good structure here? It means, okay, for those who know BV spaces, for instance, you could say that I mean, if M is in BV, then you're good to go. You can prove this thing. For those who don't know, you can just think of something like with some jump set that is 1D, and when you zoom in at one point of the jump set, you really see something that looks like just this two constants, right? An M minus, an M plus here. And right, so the problem, you see what it is here I'm assuming a priori I know something about the limit, and in fact I don't know it. So this is the whole issue here. And yeah, the problem is why is it still an open conjecture? Is because not enough is known about what the limit looks like. So today, what the result I want to tell you about is really just a small addition to all the knowledge people have accumulated about this kind of this limit M, and why it could be interesting. Let me also say that the fact that you have this cubic energy is very bad, because basically it's telling you that if you do many very small jumps, you can accumulate a lot of them, right? Because the cube, it costs not so much when the jump is small. And this is the reason why, for instance, you don't know that the limit is in BV, because you have this cubic power here. Okay, so now let me introduce this. Not that I have motivated why it's interesting to look at solutions of this equation that are not just the viscosity solutions, but for instance solutions that come from such a process here. Let me introduce this entropy productions. So entropy productions, what are these? They are not related to thermodynamical entropy, right? Just mathematicians decided to call them in analogy with entropy productions in scalar conservation laws, which maybe are connected to thermodynamical entropy, I'm not sure. Anyway, it's just something that is able to detect singularities. And in that sense, it's something detecting wild behavior, right? So that's, I guess that's why we call them entropies. Sometimes they're also called calibrations. So it's a tool to detect the singular set without knowing a priori that it has this good 1D structure, right? So, so what is it? I'm going to do some algebra. So let's take a function which is smooth on S1. So S1 is just the unit circle. See my maps M, they have values into the unit circle. And so I'm taking now a function that it goes from the unit circle into R2. And I will say it's an entropy if and only if, well, there are two characterizations. One that is just like an algebraic definition, say, if some condition is satisfied. You take phi, you look at it with respect to your variable in the circle, you differentiate, and you ask that this derivative is perpendicular to the radial vector. Okay, why not? But this is not what you want to record here. This is why is that the definition? It's because this is exactly the condition that allows you to say that if you take phi of a solution and you take the divergence, then it's again divergence free, and that will be okay if M is a smooth solution of the equation. Okay, so if you stop to think about this, my map phi here, this is something non-linear, right? So there is no reason in general that if you take the divergence of phi composed with something which is divergence free, this is again divergence free, right? But since my M, I'm assuming it is smooth, I can just apply the chain rule, compute this thing, and I realize that if I add this condition on phi, then in fact this is true. So what does it mean? It means if I have a solution without singularities, then I won't see anything here. But the point is, as soon as I have singularities, something will happen here. And this I'm always allowed to define, right? This is just the divergence of something. In the sense of distribution, I'm always allowed to define this. So without knowing a priori anything about M, I will be able to define this, and this is what will detect my singular set. So this is the idea behind these entropies. In fact, this is not really the way they arise for the first time. I guess they arise first as calibrations in a paper by Jin and Kohn, but I would like very much to have time to explain all of this story, but I don't think I have. And so let's try and understand a little bit more what happens if you apply this, but to a solution that has singularities. For instance, okay, I said I want to use this when I don't know that M has this nice structure, but just to know what could happen, let me try and do this when M has a good structure. In that case, so by good structure, again, I mean that kind of assumptions. In that case, I can still compute this thing. So where in regions where I have no jumps, I don't see anything, right? This is the same thing that happens here. But as soon as I have a jump, okay, say it's in the direction of this normal vector nu here, this will cost me something like that. And this will cost me something like that, but this will be all concentrated on my jump set, right? And so this is something I can just compute, right? I have some phi, I can just compute shift everything, and so say this is a function, cost function C that depends on the choice of my entropy phi, and that depends also on my direction here, and on my two vectors on each side of the jump. And the nice thing that's going on here is that here, in fact, you see again this cubic power appearing. So you can show that this thing, if you take its absolute value, it's actually less controlled by the cubic power of the jump. And this, when I read something like that, this is up to a multiplicative constant that depends actually on my entropy phi, and that's it. All right, so this is telling you that this is the kind of thing that you expect to be able to control with the energy, right? Because my energy was exactly the cubic power of the jump. And in fact, so here I assume that it has a good structure, and I see this is controlled by the energy. And in fact, you can really prove that this is controlled by the energy in general, even if you don't assume that you have a good structure. And this was I think, realized, I mean, first for this particular choice of particular calibrations in that paper by Jin and Cohn, and then for general entropies like that in the paper by De Simone, Cohn, Otto, and Müller, where they prove also the compactness here. And the statement is the following. So if you don't know that you have a good structure a priori, but what you know is that you are the limit of someone which has bounded energy, right? Then in fact, you can show that the divergence of phi of m, so this object here, which is a priori just some distribution, is in fact a distribution of order 0 that is a measure. So when I write m, I mean a measure. I'm really sorry for those who don't know what is a measure, but like examples of measures are Dirac masses, or like this kind of thing, just a Dirac distribution that jumps along a 1D jump set, but it could be wider too. And then so if you know that your limit of something of finite energy, then this thing, this divergence of phi of m, is a measure for all entropies. And in fact, you have this control that if you take the measure, you apply it to your domain omega, then it's controlled by something that depends on the C2 norm of the entropy times this energy. Okay, so now we know something more about the limiting solution. We know that in fact it's not just any weak solution of the eikonal equation. It's something that has this weird property here, that all divergences of entropies, so those are the entropy productions, are finite measures. Okay, so obviously when you first see that, this is not that easy to understand, because this is a set, a nonlinear set of nonlinear functions. Maybe it's not that easy to understand what that exactly means on the solution. Although you see that it does give you some restrictions, so which is good news, right? And let me tell you what we showed with Francesco. So now what we said is, okay, let's forget about the energy, the limit, everything. Let's just look at solutions which have this property, right? And which are the solutions of my title, the ones which have a finite entropy production. And so this is the result. So let us assume we have a weak solution. It's always the same equation here. then I'm saying that this thing, that the entropy projections are finite, is actually equivalent to some linear condition, which is just to have some kind of regularity, which is in a Bezoff space. Probably many of you don't know what a Bezoff space is, but I will write down something that does not use Bezoff spaces. So this property here, that the divergence of phi of m, so entropy productions, is a measure for all entropies. This is equivalent to something like that. So this is equivalent to my map M having 1/3 of a derivative in L3 in some weak sense. So I wrote down this integral. Let me just give you try to explain what it means here. So first I have this lock here because our result is really local, so we don't go up to the boundary. So this means this measure is only locally finite, and the equivalence is with I'm integrating in any subdomain compactly embedded in this domain here, right? And here, what am I saying is that this condition, this very non-linear condition, that all entropy productions be finite, if I know in addition that, if I know a priori that also my M is a solution of this equation, then in fact it's equivalent to M. So what is this? I'm taking increments of M, and I'm dividing by this 1/3 power of the increment. So I'm saying in some sense I'm measuring 1/3 of a derivative, and I'm taking this in L3, right? And I'm asking for this to be finite. Okay, so those things are equivalent. So for those who want to see a Bezoff space, this is actually this space here. But anyway, the important thing is that you have this kind of thing. You should really think of it as knowing that your solution is not just any solution, but it has some regularity. It has 1/3 of a derivative in L3. So this is the result I wanted to tell you about. I'm not sure I have time to tell you something about the proof, so maybe I should stop here.
You still have 5 minutes.
Oh, okay, then I will tell you a little bit about the proof. So obviously there are two sides to this thing. You have to show that if you know that all entropy productions are finite, then you have this Bezoff regularity, and also the opposite direction. So in fact, the opposite direction, if you know you have some regularity, then you know that entropy productions are finite. It's just a minor adaptation of an argument by Radu and Camilo de Lelis, which is based on commutator estimates. Which actually were used first on the Euler equation, I think, where if you know something about the Euler equation, you know that also this 1/3 of the derivative is something important there, related to Gonzaga conjecture, right? So this is okay. This is why this 1/3 pops up here also. And okay, that means so. As I said, this is really taken from this paper by Camilo de Lelis and Arnaud. And the idea is okay. The problem here, what is the problem? If I want to compute this thing, the divergence of phi of M, I'm not allowed to use the chain rule because I don't know that M has enough regularity to do that, right? So what you do is, okay, I will regularize my M, and then I will be able to apply the chain rule. Okay, so let's regularize M. Then you can compute the divergence of phi of M, and you still have that this M delta is divergence free, but you don't have this anymore, right? this was a nonlinear condition, so it's just approximately 1. So it's not a solution of the equation anymore. So when I compute divergence of phi of m delta, I won't see 0 anymore. I will see something that is small, and small depending on how big, how bad that almost equal is. And this is where this commutator estimates come into play, because I have to estimate the difference between this and this. You can see it as a commutator because this one is first I apply the modulus to m, it's of modulus 1, and then I do the convolution, doesn't change anything. And here this is first I do the convolution, then I apply the modulus, right? So the point is, if you have enough regularity like that, then you can actually estimate this error precisely, and what you get is that you are able to bound the divergence of phi of m delta, and then you can pass to the limit. So this is the idea, and really it comes from this fluid dynamics things. Still some minutes?
2 minutes.
Okay. And then the other side relies on many ideas by many smart people. The first idea is to use something called the kinetic formulation of the equation. The kinetic formulation is basically a way of representing characteristics. Perhaps you remember at the beginning I told you if you have smooth solutions, then the information travels along characteristics. And the kinetic formulation is a way to kind of express this property, but for weak solutions. So I won't go into more details here, but it was introduced for scalar conservation laws by Lyons, Pertame, and Talmor in the 90s. And then Jabin and Pertame, they realized you could use this also in the context of this equation. And our kinetic formulation is an adaptation of there. And so once you have a kinetic formulation, you can use the tool called averaging lemma, which is something that once you have a kinetic equation, you can deduce some regularity about it by this type of averaging lemmas. So here, I'm sorry, I'm very vague because I just don't have time to tell you more about it. We were using like a new type of averaging lemma that was devised by Goltz and Pertame in 2013, where they were able to get that kind of regularity for the Burger's equation. And so we basically adapted the arguments to our setting and to this different kinetic formulation. And just one more word. In fact, okay, this looks fancy and all like big words, but what is really behind this is the theory of compensated compactness, which is basically just the fact that if you have you have two vector fields x and y, and you know that one of them has zero divergence, and one of them you control its divergence, then you say that x, since it has zero divergence, it's gradient rotated. No, because here this is like this is a determinant.
Stretch.
Yeah.
Mm-hmm.
Yeah, right. So if it was a scalar product, I should take the curve here. So basically, yeah, you can estimate that kind of thing. And in fact, you can also estimate things a little bit less well if you just know that you control both quantities, both divergences. And if you play with this kind of estimates and with my entropies, which I know I control the divergences, then you can estimate like things like I take increments of phi of one entropy. I take another one. I also take the increment, and I will be able to control those things. And the magic that happens here is that, in fact, if you play well with the entropies you choose, and if you take good linear combinations of them, this thing also control. Okay, this is becoming very messy here. This thing also will control the cubic power of the increment of n. This is what we use. And here, this is really like a really smart thing, like to understand like how to play with those entropies to get some control. And now I'm stopping.
Thanks, Xavier. questions? Yes.
So what about the measure of omega? Can you also get the global bound of the measure?
So in fact, if I assume here, so one direction is actually works globally, and this is the one I guess you are thinking of. Is if I have this globally, then I am able to control the divergences globally, if I'm not mistaken. Okay, I should check again. I know one side works and the other side doesn't work, and right now I'm not sure which one, but okay, maybe I can tell you again later. But one side is actually global, we can do it globally. No, but it's this side. Yeah. And the other side, what we are not able to get is the full regularity up to the boundary.
Other questions? So in fact, so if you have a map, a solution that satisfies this, is it a finite energy, limit finite energy configuration?
No, that's the thing. I mean, this was just an implication. So if you know
right,
you are limited, if you know you are limited of finite energy, then you have like those conditions.
The other way around.
But the other way around, so what is done, I mean, basically the only thing people have tried to do is to just do the convolution and check if it has finite energy.
Yeah.
And if you do that, you need 1/2 of a derivative and not 1/3. So you cannot really, and I don't know of any other way right now to construct just sequences of finite energies.
Mm-hmm. So that's not known.
Yeah, that's not known.
Okay. Yes.
At the beginning, you mentioned that the relevant systems, the magnetic ones and also soft matter ones. So my question is, if I understood correctly, how here you put an energy bound on essentially on a barrier, right? So essentially on a line region between two. In physics, I would call them domains. Maybe I use the wrong language, right?
No.
But what thinking from of the magnetic system and so on, so people very often worry about, say, lattices of, say, defects or so, right? Right. So in this cases, they don't usually think about domains, but it's rather that the formation spreads out also throughout your, say, 2D plane. So I was wondering how this talks to one another. Maybe I didn't use a good
No, I'm not
language.
sure understood. Are you talking also about point defects or just line
so I
defects?
mentioned like in magnetic systems, right? So,
So of course, I mean, the thing with this energy is that it does not see point defects. So I said this is like related, but in fact, in the micromagnetic case, you would like to see point defects, and this energy does not see them. And a similar energy has been investigated by Xavier and Sabatier, and they have similar results. But in fact, in their cases, things are a little bit more easy, and they can characterize the limit and everything. But yeah, you're right. It was just like similarity, but you cannot really use to describe, I guess, what you're asking for in micromagnetics.
Because the scaling there, so in the energy, so right before we always had gradient squared plus 1 over epsilon squared, the potential, okay? So here you multiply with epsilon. So the energy of point defect is like log, but then you will kill it, it's like log epsilon times epsilon, so that goes to 0. So you don't see it. So these are called zero state, zero energy state. So yeah, so this is really to see the lines. So you have to go to.
Okay, thank you.
Other questions? Thanks you back once again. Okay, so hope you are not tired for the third talk of David.